Okay, so we've gotten to hear a lot from the optical side of the Aurora, which is fantastic. But from the radio side, there's a radio side of the Aurora too. And ham radio operators are used to working with what we call active signals. So we're often transmitting signals, but believe it or not, the Aurora creates its own natural signals, natural radio signals or emissions as well. So now we're going to hear from Dr. Jim LaBelle. And Jim, he's an experimental space physicist from Dartmouth College. And he's a professor there, and he's been at Dartmouth since 1989. He earned his undergraduate degree in physics from Stanford University, followed by a master's and doctoral degrees in applied physics from Cornell. He did his postdoctoral work at the Max Planck Institute for Extraterrestrial Physics in Germany and at Utah State University in Logan, Utah. He is a member of the American Geophysical Union and the International Union of Radio Scientists, and he has had visiting fellowships at the Max Planck Institute for Extraterrestrial Physics and at the University of Sydney in 2008. In 2010, he was appointed to the inaugural Lois L. Rogers Professorship at Dartmouth. So I'd like to welcome Professor Dr. Jim LaBelle, who will be talking to us today about observing radio signals of auroral origin. And this is another invited tutorial. Thank you, Jim.
Okay, thanks very much. Can you hear me all right?
I can hear you just
You're,
fine.
you're coming through fine, Jim. Hi, it's from
Okay, let me
Phil.
go ahead and get my slideshow going here. All right, so what I wanted to do was start out by, I added a slide actually at the last minute after Dr. McDonald's talk, because I realized there's some confusion about radio aurora versus auroral radio emission. So radio aurora usually refers to the scattering of radio waves off of auroral structures, for example, with coherent backscatter radars, but also possible with ham radio. Auroral radio emission is a slightly different topic. It's the spontaneous emission of radio waves by plasma physics processes in the aurora. So I think of it as the aurora directly talking to us. And it's also possible to observe with ham radio. And so my talk is going to be focusing on the auroral radio emission rather than the radio aurora, just to make a distinction here. Both are potentially of interest to ham radio, of course. So now back to my first slide, I want to just point out that for some time, scientists have been making observations, of radio emissions in the aurora using equipment or instrumentation that's very familiar and similar to what ham radio people use. I mean, I'm guessing that many people in the audience use antennas that are very similar to these ones shown here. Here's a picture from a manual, operations manual by Mike Trimpe, showing the typical type of antenna that we use in our observations of radio emissions from the aurora. Typically, it's sort of a 3 meter on a side, 10 square meter single loop magnetic antenna on a mast. And often we employ 2 perpendicular ones to get polarization, and quite often an array of 3 to 5 or more of these things in order to also do direction finding. A key component of this system is the active preamplifier that you see at the base of the antenna here. And so I have a slide on that. This is our active preamplifier design. It's designed to have a flat response out to about 10 megahertz or so, and optimizing, of course, the current and voltage noise of that first stage operational amplifier, reducing as much as possible resistor noise. It includes accommodation for a calibration signal that can either be injected externally in this version of the preamp, but we also have versions of the preamp in which the calibration signal is generated in the preamp. One reason I bring this design up, first of all, I'm guessing this preamp design is very similar to active preamplifiers used in the ham radio community. But I bring it up and show it here specifically because I want to emphasize that we're happy to share this or any aspect of our designs with anyone in the community. So if anyone would like this design, just email us, myself or David McGaw, the engineer who works in our group and who's also a ham and at this conference. And we'll get you this design. We may even have a slew of boards, I don't know, or maybe we can order some. But we're happy to help facilitate measurements by amateurs with however we can. And of course, probably I'm guessing people already out there have preamplifiers that are of comparable performance to this. By the way, this preamplifier has also been published in a ham radio handbook. Let's see, moving on to the overall system. So, you know, up to about 10 years ago, scientists deployed specialized receivers that were typically built in university laboratories and were fairly different from what amateur radio would use. However, in the last 10 years, there's been a convergence between scientific instruments and the receivers used by amateur radio. And so, you know, nowadays, the measurements we make, typically you have some kind of anti-aliasing filtering on the front end, but then, you know, drop in your favorite software-defined radio down here. You know, in some of our applications, we actually have a A to D receiver and we use custom signal processing software. But in other cases, we also use USRP receivers or SDR14 or these new dongle receivers we've used. So, you know, we're using, essentially there's been a convergence, and we're using the same equipment that amateur radio people are using to make our measurements. And it kind of emphasizes that, you know, ham radio hobbyists can make these measurements. I show a picture here of one of our instrument deployments in Churchill, Manitoba, and you can see it looks just like your typical ham radio shack. So that's something that to take note of. Okay, the catch is, of course, that to observe the radio emissions coming from the Aurora, you have to be, you know, near the Aurora. That is in the far north in general, since the Aurora in the southern hemisphere is not very accessible. And this map shows, what this map shows is the red line here is the typical position of the midnight Aurora. It's 65 in magnetic latitude. And the midnight Aurora is the most active time for observing radio emissions. And so it's appropriate. And that's the typical position. And so, you know, you want to, ideally, if you want to make regular observations of radio noise coming from the Aurora, you want to be near this red line. In fact, you really ideally want to be poleward of it. The blue and red, the red stars and blue dots here show locations where scientists have set up observing stations over the years. And the red stars are the really primo locations. And you'll notice that those are actually to the poleward side of the typical Aurora. And the problem is that if you are directly under the Aurora, you know, these radio emissions from the Aurora are happening, but the Aurora creates all this ionization in the E and D regions that screens you or absorbs the emissions from reaching you on the ground. And so where you really ideally want to be for many of the radio emissions, you want to be 100 to 500 kilometers poleward of the Aurora in a region we call the polar cap, where you have a lower density, more laminar ionosphere. And so you can actually, you know, observe these auroral radio emissions. They come out of the Aurora and they reach you on the ground through this kind of lower density laminar ionosphere of the polar cap. And so that's actually the ideal thing. For many of the auroral radio emissions, it's actually ideal to be a bit poleward. This is, of course, unfortunate for amateur observations because it's even puts you in more inaccessible locations. I will say there are some of the types of emissions, though, that I'll talk about that can be observed, you know, even under the Aurora or even perhaps equatorward of the Aurora. And the other thing that's worth noting is that, you know, this location here shown on this map, this is the typical location of the midnight Aurora. But of course, the Aurora varies a lot, you know, depending on the sun's activity. And so, you know, a few times a year, this typical position will be over the northern United States, over Hanover, New Hampshire, or close to it. So, you know, that if you're an amateur wanting to measure these auroral radio signals, you kind of have two strategies. You can either go up to the north, or you can wait for those few days per year when the Aurora comes to you. And let's see, if you go up north, you know, where are the most accessible places for amateurs to maybe take a trip and go up there? Certainly Alaska is probably the easiest place to reach because you can fly relatively inexpensively to Fairbanks. And then you can drive there. A couple of gravel roads. There's, of course, the Pipeline Road. And there's also another road that goes up to a place called Circle Hot Springs in Alaska, which is about 100 kilometers north of Fairbanks. And, you know, along those roads are good possibilities to get a bit poleward of the Aurora and have good observations. You just have to not tell the rental car company what you're doing. That's all. I will also point out that, let's see, we have, that you know, for most of the auroral emissions, you have to go, you can't go in summer because, you know, sunlight also causes the same D and E region issues with observations on the ground. And so, you know, the best time to go is probably spring or fall, very good times to make auroral radio emission measurements, or the dead of winter, okay? And there are some types of emissions that can be observed in summer. Okay, so that's a little bit of an upshot about what you're up against, you know, as an amateur wanting to make these measurements. It's not impossible though. And, you know, I would encourage people to plan trips. Okay, let's see. I wanted to say, how do we select our frequency range for observing? Well, first of all, I'm talking here about radio emissions that are in the range where, in kind of the ham radio band range. And so this means lower HF or MF frequencies. And so at these frequencies, it's the electrons, not the heavy ions, that are involved in the emission of the radio waves from the aurora. And there are two primary resonant processes, types of resonances that happen with the electrons in the aurora. The first one, illustrated on the left-hand side of this plot, it only occurs in a magnetized charged particle gas, and of course we have a magnetic field in the aurora. And what this is the cyclotron resonance. As you know, an electron in a magnetic field will undergo helical motion, circular motion if it's exactly perpendicular, going exactly perpendicular to the field. And this circular motion has a period which is dependent on the strength of the magnetic field. It's called the cyclotron period, and the frequency, associated frequency, is the cyclotron frequency. Okay, in the aurora region, the cyclotron frequency is around 1.5 megahertz. So that's one of the critical resonances in a charged particle gas. The other critical resonance is called the plasma frequency. And for this one's attempted to be illustrated by the middle panel here. And the idea here is you have your heavy ions, which, you know, hardly move compared to the electrons. So you imagine taking in your charged particle gas, you imagine taking your electrons and offsetting them away from the ions. They'll clearly, because opposites attract, the electrons will come back towards the ions. They'll be attracted back, and they will overshoot and then be attracted back again. And so the electrons will oscillate around the ions. This is called the plasma frequency. And this resonant frequency depends on the density of the charged particles. And the higher density, the higher the frequency. And in the ionosphere, for ionospheric densities, this is highly variable, but this plasma frequency resonance can vary between 1 and 10 megahertz. And by the way, the plasma frequency is applicable to motion of the charged particles along the magnetic field. Perpendicular to the magnetic field, the resonance is slightly higher, not very much higher, in the same frequency range. But the upshot is that, you know, these resonances occur in the range of 1.5 megahertz and maybe the harmonics, and 1 to 10 megahertz. So this kind of tells you the frequency range that's going to be of interest, right? Because these resonance frequencies are where the charged particles of the aurora are going to interact strongly with the electric and magnetic fields and produce these radio signals that we can observe from the aurora. And so this pegs the frequency range for you. You can sort of expect that if you go in looking at kind of, you know, from 100, our measurements typically are from 100 kilohertz up to 5 or 10 megahertz. That band you can kind of predict is going to have some interesting things in it. Okay, so what do we see? All right, well, here we have a waterfall chart. I'm thinking that most people in the audience are familiar with these. So, you know, this is a chart where you put frequency of the radio signal on the vertical axis, time on the horizontal axis. Here we have 0 to 5 megahertz on the vertical and 1 hour of time on the horizontal. These measurements are made in northern Canada. 6:30 UT corresponds to about midnight local time. I mentioned that midnight is a prime time to be observing these emissions. And, you know, on this kind of waterfall plot where dark pixels represent a strong signal at a given frequency and a given time, and light pixels represent weak signals being received, you know, horizontal lines represent man-made signals typically, right? Because humans like to transmit on a fixed frequency. And so all of these horizontal lines represent man-made signals. And you'll notice there are a huge number of them between 550 and 1600 kilohertz. Well, that's our familiar AM broadcast band. And very interestingly, you notice that right at about 0650 UT on this particular day, those signals faded away very promptly. except for a handful of them. And what's happening here, this is a typical signature of something that was referred to in Dr. McDonald's talk, an auroral substorm. The onset of an auroral substorm, when the aurora breaks up and covers the sky and generates ionization over a large region, what you get is you get absorption of these distantly propagating radio signals that are propagating by bouncing off the ionosphere. And so that this is evidence that there's an auroral substorm going on when you see this kind of fading. The unaffected, the local stations are the only ones that are unaffected by the fading. So anyway, you can see the man-made signals, but you can also see on this plot several signals that are clearly very different from the man-made signals. And these signals, which have different characteristics, are not constant frequency. These are the emissions coming from the aurora, signals of auroral origin. And there are three basic types that we see. One reason I selected this hour of observation is that we see three different types during this hour. The first is what we call auroral hiss, okay? And these are wideband kind of impulsive emissions that occur below 1 megahertz, okay? You see them down there. And then the second type we have are called auroral medium frequency burst, and these are also broadband emissions, and they are occurring though at a higher frequency. They have a bandwidth maybe of 1 or 2 megahertz, and they're occurring above about 1.5 megahertz. And notice there's a strong correlation between the hiss and the burst. That's quite commonly observed, and also both the hiss and the burst are happening at the substorm onset time. That's very interesting also. That's characteristic of these emissions. And furthermore, you'll notice that well, let me just mention the third emission. The third emission is called auroral roar, and it's in contrast to the other two, it's a relatively narrow band emission, only about 100 kilohertz bandwidth, which is, maybe not very narrow band compared to most ham signals, but we consider it narrow band for an auroral signal, and near about 3 megahertz. By the way, 3 megahertz is about twice the 1.5 megahertz, which is the cyclotron resonant frequency. Remember, one of those two critical resonant frequencies in the charged particle gas. This emission occurs at twice that frequency. So these are the three types of emissions. By the way, one thing that's interesting to see is that, you see this auroral roar, for example, occurring before the substorm onset, and then after the substorm onset, it becomes rather intermittent. You just see blips of it. And in fact, all of the emissions seem to disappear shortly after the aurora expands. And you might ask, what's going on there? Well, what we strongly believe is that these emissions are still occurring, up in the ionosphere. And what happens is that the aurora expands and creates all of this ionization that screens the ground observer from the phenomenon. So this is quite typical that we see we get good observations of the radio emissions up to the onset of the strong aurora. And then the aurora kind of turns off the emissions on the ground. The emissions are, of course, still going on upstairs in the ionosphere. Okay, what I'd like to do is spend a few minutes, if I can, hopefully I have enough time to do this, to talk about, each of these types and some of the interesting things about them that can be observed, and maybe that'll inspire some types of measurements that amateur radio hobbyists could make. So let's first talk about the roar emission. First of all, the roar emission is not just at twice the cyclotron frequency, 3 megahertz, but it also occurs at 3 times the cyclotron frequency, which is near 4.5 megahertz, and also near 4 times, here at 5.5 megahertz, and even 5 times has been observed. So all of these harmonics have been observed. The most commonly observed one is the 2FC, the twice the cyclotron frequency, but these other ones are also observed. One thing interesting about these harmonic emissions is that the higher emissions, the 4 and 5 FCE emissions, occur favorably during the daytime, okay? Whereas the 2 FCE emission, the 3 megahertz emission, occurs favorably at nighttime. And one way to illustrate this very clearly is to go to South Pole, okay? So scientists have made observations of these emissions at the South Pole of the Earth. The South Pole has this huge advantage that the day lasts a year, okay? So night is 6 months long, day is 6 months long, night is 6 months long. And what's shown on this graph is 2 years of data on the horizontal axis and frequency of observed roar emissions on the vertical axis. The green is the lower bound of the observation, the red is the upper bound. And you can see that and by the way, the gray corresponds to time when no measurements were made, when the equipment was being used for other experiments. But what you can see is that during the nighttime, you get the 3 megahertz, or somewhat at South Pole, somewhat lower than 3 megahertz emissions, okay? And then as twilight, daytime sets in, you start to get the 4 megahertz emissions. And then as the sun rises higher in the sky, you get the 5 megahertz emissions. And when you get midsummer, the sun highest in the sky, you have the 6.5 megahertz, 5 FC emissions. And then you have that same stair-step pattern as the sun sets, you know, and then the stair-step pattern repeats in the subsequent year. So, you know, this is kind of very interesting. It shows that these higher harmonic roar, these higher harmonics occur during the daytime. They require daytime. The lower harmonics occur during the nighttime. And this actually accords very nicely with the theory of how we believe these emissions are generated. And the idea behind these emissions, how they're generated, is they're generated at what we call the double resonance condition. I mentioned there are 2 resonance processes. There's the cyclotron resonance, which is the electron going around the field line. And there's this plasma frequency resonance, which is offset the electrons from the charged particles and they oscillate. Okay, now shown in this graph right here is altitude on the vertical axis, frequency on the horizontal axis. And what's shown here are, first of all, these 3 lines right here. They represent the cyclotron frequency, the cyclotron resonance frequency, and its harmonics. Notice that the cyclotron resonance frequency decreases with altitude because remember, it's dependent on the strength of the magnetic field, and the magnetic field decreases with altitude. So these 3 lines here represent the cyclotron frequency. It's 2 times the cyclotron frequency. This should be 3 times. That's a misprint there. This should be 3 times the cyclotron frequency. The other lines here represent the other resonance, the plasma resonance. Remember, that resonance depends on the density of the charged particles. So it has its maximum value right smack in the middle of the ionosphere at about 350 kilometers altitude. And it goes down above that and below that altitude. And here's the thing about the auroral roar emissions. They occur at the very special conditions, the so-called double resonance, where these 2 resonance frequencies overlap and you get a maximum of interaction between the charged particles and the electric and magnetic fields. And that's where these roar signals are generated. That's why they're relatively narrow band, okay, because they're just coming from one particular height. They're basically these hot spots in the ionosphere, okay, and where the resonances interact. And when you get the aurora, when you get these charged particles that Dr. McDonald talked about coming down the field line generating the aurora, those charged particles at this double resonance generate these strong radio waves that then propagate to the ground, and we observe them. And we observe them at harmonics, near 3 megahertz, near 4 megahertz, and so forth. Now, here's the key thing, is that you can see which harmonic you observe depends on how high your electron density is in the ionosphere. At nighttime, the electron density isn't very high, so you only have the possibility to have this lowest double resonance, okay? But during the daytime, the electron density is much higher due to photoionization. And so you have the possibility to have the double resonance occur with the 4 and 5 harmonic cyclotron resonance. And you get these higher frequency emissions. So anyway, the reason this theory fits perfectly with the observations that you see the high harmonics during the daytime, the low harmonics during the nighttime. One sort of mystery is why you always tend to see just one of the harmonics, just the highest one that's possible to observe. We still don't quite understand why that is. It's interesting. One thing I will mention is that because these higher harmonics are observable during the daytime aurora, they represent, I think, a good target for amateurs, because I think you don't need to be, poleward of the aurora, hundreds of kilometers in the polar cap to have good propagation conditions to observe these. These things are well above, frequencies that would be absorbed by the D region. And so you could observe these maybe even equatorward of the aurora. I think these might be a kind of target that amateur radio hobbyists might look for if the aurora comes near your location or if you get the chance to travel north. Let's see, I thought I'd say a few words about another interesting thing that amateurs radio might want to focus in on if they happen to observe these natural signals from the aurora, these roars, is that it turns out, if you look on a poor resolution plot like this top plot, the roar doesn't look very structured. It just looks like a blot on the waterfall chart. But if you look with higher resolution, you see that there are all kinds of fine structures in these Aurora emissions. And those are interesting to observe. And ham radio, amateur radio equipment could easily detect these structures. What you do is you set a down converter with a center frequency within the frequency of the Aurora emission, and then you shift an audio bandwidth down to baseband, and then you can detect these fine structures, and you can listen to them. Let's see, I have some more here. I think I can play these and then we'll listen to them. So here are some typical, remember, these are just little snapshots of the Aurora emission. These are 10 kilohertz bandwidths, audio bandwidths that are selected from inside of the Aurora emission, which is itself is 100 kilohertz bandwidth wide, but we take little sections of it. Let's listen. That beep, by the way, was an artificially injected beep, but you could hear the emission around that. Here's another example. Here's a strange one here. You see this kind of sinusoidal varying structures. And I'll point out this bottom one, okay? So this is kind of these multiple structures again. By the way, if you like what you hear, you can go watch the IMAX movie, Solar Max, which was filmed by one of our colleagues, Robert Ether. And in this movie, which I recommend, when the Aurora comes on, the sounds that you hear are the Aurora sounds from our laboratory. So anyway, just a plug for Robert Ether's movie. By the way, what causes these structures? I might say a word on that, on what the physical mechanism is for these fine, frequency structures in the radio emission. Well, here's what's believed to be causing them. It turns out the Aurora is highly structured. The auroral ionosphere, the electron density is not very laminar. It's highly irregular. And it's irregular both because the electron precipitation coming down is filamented, and so it creates irregular density by impact ionization. But it's also irregular because of internal plasma instabilities to the plasma that create irregularities. But basically, you get irregularities on all different scales, and these irregularities tend to be aligned with the magnetic field because charged particle transport is rapid along the field and slow across the field. You tend to get these tubes, basically, of enhanced or decreased charged particle density. And if one of these tubes has a dimension that's comparable to the wavelength of the radio wave or the waves that are being spontaneously generated by the Aurora, then what can happen is that the waves will be discrete in their structure. In other words, they'll be trapped in that, and they'll make like standing waves inside these tubes of enhanced density. And you won't get just arbitrary frequencies of waves. You'll get certain discrete frequencies selected. It's very analogous to a drum head. So, the drum head is fixed at the outside. When you pound on the drum head, the variations in the surface are superpositions of sort of normal modes that are defined by the area of the surface and the tension and the boundary condition. And so you get and it's very similar, so when you pound on the drum, you don't get just a continuum of frequencies. You get certain frequencies that correspond to these normal modes. Well, it's the same thing in the waves being generated by the ionosphere. So here's the idea. If you look at the upper left, you have your magic hotspot in the ionosphere where the radio waves are being generated. If you have irregular density that's comparable to the wavelength of the waves are not arbitrary in frequency or continuous in frequency. Certain frequencies are selected that fit kind of in the cavity. And then that frequency discretization is then maintained, is transmitted in the emitted radio emission, and what you end up with is all these little fine structures in the radio emission, and they vary. The frequencies vary and the spacings vary according to the kind of evolution of these tubes of plasma that are causing this interesting fine structure. So this fine structure is something that's very interesting that could be observed with amateur radio, and it relates, in principle, you could relate this back to the structure of the density in the Aurora. Okay, let me move on and talk about briefly the other emissions. Okay, don't want to skip them. So let's talk briefly about the medium frequency burst emission, right? There's a broadband emission, and it's often seen at the same time as the auroral hiss emission, which is also broadband, but at a lower frequency. So let me tell you about these. So first of all, this really emphasizes to you that these emissions, unlike the Aurora emission, these emissions happen for a very short time, right at the onset when the Aurora has this pattern of activity called a substorm. And right at the onset of the substorm, when the Aurora breaks out and shifts poleward and equatorward and covers the sky, it's right at that onset when you observe the EMF burst and the His emissions. This is a several-hour waterfall chart recorded at Churchill, Manitoba. And what you can see, notice the Aurora emission here happens all along. You know, it can be observed for a long time. But the burst emission and the His emission are very concentrated for just a few minutes, right around the time of the onset. How do we know it's the time of the onset? We have magnetometer data down here, and the magnetometer data undergo a very characteristic signature, okay, a negative bay, right at the time of that onset. We also have rheometer data, which is absorption data that tells you the time of the onset. And, you know, one thing that's interesting, you know, again, you'll notice the emission only lasts for a couple of minutes and then appears to turn off. Of course, we think it doesn't really turn off at that time. It's still happening, but what happens is the same ionization that's causing this rheometer signal down here is basically screening us from seeing the emission. We see it for just a few minutes at the start, but then the Aurora overcomes our station and we don't see it anymore. One evidence of that is this data right here. Here are observations of medium frequency burst emissions, okay, from a chain of observatories in Canada, ranging from sort of Gillam at 67 degrees up to maybe 79 degrees up here, okay? And what you can see is, remember what's happening here is there's a substorm onset happening a little after 0500 or right around 0500, okay, UT. And this in this onset, the Aurora is expanding poleward. And so, you know, right at the onset, if we're sitting at Churchill, we see these medium frequency burst emissions. We also see them at Arviat, which is 100 kilometers north. But as the Aurora expands poleward, it first overtakes Churchill, and the emissions turn off at Churchill. They're still going on. How do we know they're still going on? We see them still from Arviat, further north. But they've been erased at Churchill because there's strong ionization overhead that wipes out the signals before they reach the ground. And then when the Aurora reaches Arviat, all of a sudden it wipes out the signals there. But they're still happening. How do we know? 100 kilometers north of Arviat, we see them happening up here at Baker Lake. A little while later, the Aurora expands poleward to Baker Lake and so forth. So this is kind of an evidence of what's going on here with these radio signals and why it's helpful to be, for this particular type, it's helpful to be poleward of the Aurora. Here's another evidence of that. Here's an EMF burst emission. Notice the frequency. It runs from about 1.5 to about 2.5 megahertz, kind of broad band here. Okay, only lasts a few minutes. But we observed this one in Toolik Lake, Alaska, with an array of antennas. So we were able to do direction finding. And what's shown in the right-hand plots here, first of all, on the right-hand upper plot here, this is an optical all-sky camera view of the Aurora from this Toolik Lake site in northern Alaska. And south is at the top, okay? And what you see is you see this bright auroral arc right here that stretches across the sky from west to east. And it's just in the act of brightening. This is right at the start of an auroral substorm, and the arc has brightened. And if you look down below, of course, this is the time right when the EMF burst is being observed. If you look down below, this is the direction of arrival of the EMF burst signals. And south is again at the north. We've roughly tried to make it at the top, rather. South is at the top of the plot. And you can see the signals are coming from an elevation. They're coming from the south, and they're coming from an elevation of perhaps 60 degrees or something like that, you know, from this auroral arc right here. And then what happens is that as the Aurora expands poleward, remember there's a substorm going on. So the Aurora's just set off a strong active period. The Aurora is expanding poleward. And notice that as it expands poleward, the radio emission shifts to higher elevation angles. Do you see that? And so that means as the signal's coming from this arc that's coming towards us, and we can see that in the direction finding information. And then interesting, as the arc comes overhead, the emission turns off. Okay, that's exactly what we sort of expect. This arc is now causing ionization, strong ionization right overhead of us. Okay, signals are still going on up there, but they're screened from our location. We don't see them after this. So this is a typical pattern of activity of this auroral EMF burst emission. observed, you know, and again, the ideal thing is to be somewhat poleward of the aurora to observe this one. And you get to see it right at the start of the substorm as the arcs expand towards you, and it turns off when the substorm reaches you. Let's see, I thought I'd also point out that this emission also, this burst emission is also highly structured. And so we try to show that down here. I guess we have a few seconds expanded plot. Here's the medium frequency burst. This one goes from about 1.5 up to 2 megahertz. Lasts just a few minutes, as you see. And here we have an expanded plot of just a few seconds showing that there are a lot of fine structures within this. And, you know, these are not fully understood yet. I can play a different type of sonification of this data. The sonifications I played to of the Aurora emissions before were little audio width, you know, audio bandwidths that were down converted to 0 to baseband and played for you. What I have is a different form of sonification here. To sonify this emission, because it's so broadband, what I've done is we just basically play it very slowly so that, you know, instead of 0 to 2.5 megahertz, this is 0 to 2.5 kilohertz. We just slow it way down. But then we have to do some decimation so we don't have to sit here all day to listen to it. Let me play this for you if I can bring this up. So this is the EMF Burst. Let's see, I think I'll stop it. We're about halfway through that waterfall plot there, but that gives you kind of the idea. It's kind of interesting. The burst sounds more like a roar. The roar sounds more like a burst, but I guess we're stuck with the names as they are. By the way, the burst, we don't really have a very strong idea. Unlike the roar, we don't have a strong idea what causes it, but it's believed to be related to the other resonance, the plasma frequency resonance. And it's believed to come, perhaps the wide range of frequencies suggests that it perhaps comes from a range of altitudes where this resonant frequency takes on a range of different values. Let's see, I wanted to just have my last 5 minutes. I didn't want to miss talking about what is probably the most important auroral radio emission. So all of the three that I've talked about right so far, the roar, the burst, and the hiss, are all very low power emissions, few watts per source, tiny, tiny fraction of the auroral energy, of the energy of the auroral electrons. So the mechanism that produces these is relatively inefficient. Nonetheless, even at a few watts, as you guys all probably know, you can easily detect that at a few hundred kilometers range. And so, you know, these are easily detectable with our equipment, even though they're low power. However, there's another phenomenon called auroral kilometric radiation that is quite different from this. It's an extremely efficient mechanism by which it's generated. And something like 1 to 2% of the energy of the auroral electrons actually goes into radio waves in this auroral kilometric radiation. Here are some pictures of waterfall plots of it. These waterfall plots were made from satellites. The auroral kilometric radiation is primarily observed from satellites. And so if you have a low flying satellite, the reason is that it's generated at a source region which is about 5,000 or 6,000 kilometers above the surface of the Earth, and it's beamed outward away from the Earth. Furthermore, it's in the X and O modes for the most part, and those modes can't penetrate. Even if they were to come towards the Earth, they can't penetrate because these frequencies of the AKR are well below the critical frequency of the ionosphere. By the way, the reason it's called auroral kilometric radiation is that the wavelength is around a kilometer, meaning the frequency is hundreds of hertz, hence well below the critical frequency of the ionosphere. So this is what the waterfall charts of these look like in a satellite that cruises fairly close to the source, where you can kind of see evidence of the beaming pattern, and a satellite that is much further out where you basically see intermittent emission. By the way, it's very interesting. You know, the Earth is this powerful radio source, gigawatts of power. And yet we didn't know it until the 1970s, okay? And that's because, you know, to see it, we had to get out away from the Earth with satellites and look back at our Earth to see that we're a radio source. It's interesting, we knew long before, from the 1950s, we knew that Jupiter was a radio source. Jupiter emits the same type of radiation, and we knew that long ago. That's because Jupiter, we can, of course, it's beamed outward, we can see it, and also Jupiter has a higher magnetic field, so the emissions are higher frequency and can penetrate the ionosphere. Okay, so the interesting thing, though, is that even though the space physics lore has it that you have to be in space to observe the auroral kilometric radiation, it's pretty clear to many of us that you don't. And so here are some interesting observations. The top panel shows spacecraft observations of auroral kilometric radiation from far, far out, a couple of 100,000 kilometers away from the Earth. And at that distance, the AKR just appears as these intermittent radio emissions at 200 to 600 kilohertz. The bottom panel shows ground-based observations at South Pole on the surface of the Earth. And what you see is that you see some emission structures that look very similar to the ones seen in space. So this is among the evidence we have that, auroral kilometric radiation not only gets beamed out into space, but also some small part of it, very low power part, somehow leaks back. And this is a process that's not yet fully understood and gets observed on the ground. By the way, I'll point out that we've only made, over all the years, we've only made one observation of this at Northern Hemisphere location. The problem is you have all these man-made interference signals in the Northern Hemisphere, and there's only narrow windows where you can look. But, I put this as a challenge to amateurs. Maybe you guys can get in there and look between these signals and actually see some more of these AKR examples at Northern Hemisphere. I'll also mention that AKR, like the other emissions, has all kinds of interesting frequency structure. I don't have time to talk about how it's caused, but it's something that's interesting and intriguing for amateur radio hobbyists to potentially observe. Okay, so I was going to end with this slide here, which is kind of summarizing the 4 emissions, their characteristics, and what the outstanding scientific questions are. But I realized I should rather put out some challenges to the hams. And so, on each of these, I think there are some things that, citizen science that, if amateur radio hobbyists can tune up their gear to look for these things, there's some things that would be interesting to do. So, for example, auroral hiss, one question is, auroral hiss propagates, I didn't talk about it much in my talk, but it propagates a bit more efficiently subionospherically than the other emissions, particularly as you get to the lower frequencies down towards VLF. And so the question is, how broad a range of latitudes or area can we observe these? Can you observe these well south of the aurora? I don't know, this is something maybe that ham radio hobbyists could address. AKR, I put down the gauntlet. I'd love to see, can amateurs observe this in the Northern Hemisphere? Scientists haven't been very successful with that because of the interference problem. Well, basically all the scientific observations, almost all the scientific observations of ground level AKR have been from Antarctica, where you don't have interference. But a challenge to the hams. Maybe it can be measured at the Northern Hemisphere. Aurora roar, those cyclotron harmonics. Are there even higher harmonics? Something we're looking for. Amateurs could too. It'd be very interesting to get cluster of these high harmonic observations over some area or region. What area do they illuminate? Are they observed at equatorward of the aurora? And then finally, the medium frequency burst. It's probably the toughest one to observe because it occurs in such a narrow time window, best observed poleward of the aurora. But nonetheless, I think it would be really interesting if amateur radio hobbyists could measure it, and particularly if a number of them in a cluster, I think could be very interesting. So anyway, I'll finish there. Sorry to run a minute late, but there's maybe some inspiration for amateurs to get involved in looking at radio emissions from the aurora. Thank you.
Thank you so much, Jim. That was fantastic. Just a really, really nice presentation. And I think you'll see in the chat window that the attendees and the panelists agree. I really appreciate your challenges to the radio amateurs. And some of the radio amateurs, the attendees, are already asking questions like, when you say, what do we need to do to tune up our rigs? What are some of the suggestions you have? If you were a radio amateur, what would you do to go radio auroral emission hunting? How would you set up your ham radio?
I think one key thing is to look at probably a bit wider band than most amateurs maybe normally do. Now I have to admit, I'm kind of ignorant because I'm not a hobbyist. But my sense is that typically hobbyists are looking on relatively narrow bands for specific signal targets. Mm-hmm. And, the aurora, if you can open up the bandwidth a bit. Mm-hmm. I mean, we saw the roar harmonic emissions are typically 100 kilohertz wide. the EMF Burst even more so. So I think that's one thing that maybe is a bit different from what amateurs are normally doing. The other thing is that you need relatively high time resolution to see some of these structures. You know, you can do something with taking one spectrum per second waterfall charts, but for some of the emissions, you probably need to do a bit better than that. But anyway, I think that's the main thing. And the other thing, of course, would be making sure you're sensitive enough, you know, using a good active preamplifier, and making sure you're not saturated or clipped out by strong signals in your bandwidth.
Well, I think what's nice is that we're in a very good position these days to make those adjustments to our systems. So certainly, you know, years ago when people were focused mostly on operating single sideband and we're using analog radios, there was a lot of focus on very narrow band filters that, you know, 500 hertz for CW or Morse code, you know, 2.7 kilohertz for single sideband phone. You know, but now that we see a lot more software defined radios, and even a number of the analog radios, they definitely let you open up the bandwidth there, which is really good. And certainly with our Tangerine SDR and Personal Space Weather Station project, the radio that we are working on designing will be very well suited for making those sorts of observations with both a higher time resolution, a wider bandwidth. Will be very well set up for that.
Excellent.
Yeah, so that's very exciting. Those are definitely things we can do, and I think you know, there's that Google Doc that some people are going to be putting questions into, and that was one of the questions: what can amateurs do? So maybe later you could answer some of those questions.
I'd be glad to.
Thank you. Well,